Hello, everyone. In 2010, John McLuhan wrote one of my favorite blog posts of all time, showing how to use a chicken and Mathematica to do some spy stuff. A few years later, Mercedes-Benz marketed a new S-Class with a video starring a hen. My name is Jan Brugard. I'm the CEO of Wolfram MathCore, and today I will take inspiration from the Mercedes-Benz video to illustrate some of the new features of System Modeler. Using the chicken, Mercedes-Benz introduced what they called the intelligent drive, magic body control for the S-Class. When you gently move around the hen, it has an amazing ability to maintain its head in a stable position. When building car suspensions, this is a quality you want to replicate. You want the wheels to follow the road perfectly and never lose grip, while the car body should feel stable and comfortable. To achieve this, you can use a smart mechanical solution or some intelligent control system. Whichever solution you go for, system modeling is an essential tool in the design process. I will come back to that later, but first let me go through some of the additions we've done in System Modeler and system modeling during the last year. I will mention some libraries, system modeling in the cloud that I know Steven mentioned in his talk, and then things that are in System Modeler itself. So let's start with libraries. We launched a couple new versions of OPC Classic and Model Plug in December 2020. Then in February, we released a completely new library, Business Simulation Library, which, as the name says, is used for business simulations. And by the way, whenever you see red ones here, if you have downloaded the presentation, that means there's a link, so you can go there and read more about that. So here's the blog, for instance, about the Business Simulation Library. Then in June, we released a new virtual lab called College Digital Electronics. And very soon, we will have yet another one, College Mechanical Engineering. I will not spend that much time on libraries today. What I will mention later on a bit about is system modeling in the cloud. So this was something we released in Wolfram Cloud 1.59 of all versions. So I will get back to that. And then in System Modeler, we are now with 13, which is releasing soon, including the Fluid library, which is probably the largest modeling library we have added to System Modeler ever. For this, we have a specific presentation tomorrow by my colleague Ankit Naik. So I will not talk too much about that today, but I'll recommend his talk tomorrow. What I will show is from the 12.3 and 13 is a bit of how we can better customize model plots. But my main focus will be on streamlined creation of controlled systems. And that takes me back to the chicken and the car. If we look at the chicken and the car, at first sight, they are, of course, very different. But here you see I'm stating that they are approximately similar. And in a sense of how the control could or should work, they are actually quite similar. We have the hen trying to control its head and the car trying to control the body. In order to do this, we could basically, or design a control system for this, we could basically describe the head of the hen or the body of the car like as one mass, and the body of the hen or the wheels of the car as another mass, which are then connected through a suspension system in the case of the car, and the neck in the case of the chicken. And these are sort of could be described as spring damper systems. So I will focus on the car now, and I will put the camera on top of it. So we have the same system here. This was representing the wheels, the car, and the camera. And on the right-hand side here, we see a corresponding 1D translation and model in System Modeler. So the reason why I just use 1D is that we're looking at the movement up and down in this case only to simplify our task a bit. And that's also, of course, the most important aspect for stabilization. So between the camera and the car, we have a mount. And in the case of the chicken, it would have been the neck. And the chicken would have used use its muscles to control the neck, of course, and do this, and has some sort of intelligent control system in order to be able to maintain the head in a stable position, which is what we now are trying to do with a car and a camera on top of it. I also added here a spring damp system for the wheels, which is the elasticity of the wheels, because of course these also absorb some of the vibrations from the road. Let's open this in System Modeler. There you go. So here we have the model. We can see it's the same as I showed in the presentation. And there are some hidden things here that I had prepared. And I can see there's some bug here with big text. Never mind. Still will work, I hope. So I have prepared this so I can configure this model and add a road. Hopefully you can see this, but it's basically a Boolean variable that's set to true, and I activate these components here. These components describe a road profile that includes some speed bumps and some holes. And based on that, we will have a contact point. So we drive in the car at some velocity along this road, which will give us a contact point for the wheel at every point in time. And the spring damper of the wheels, I have added a gap also, so we can lose contact with the road. And then we have the system that I just described. For the design of the controller later on, we will also need some sensors to measure different things. In this case, we're measuring the relative distance between the camera and the car, and the relative distance between the wheels and the car. So these are the two things that we will use later on for designing the controller. But before we do that, let's look at how this system works. So I'll simulate it. And immediately a model plot appears. And here we can see actually one of the new features that we can now annotate and save with plot markers that show, if I open here a bit, we can see better, they show specific values at the different markers. But we also have names for them here. So here is holes 1. So it's the first section with holes, which you can see here. The purple is the road profile. So here we have a bunch of holes. And here it says bumps. We cannot really see them here. I'll get back to that. And then we have more holes and bumps. So we have 5 sections of holes and 5 sections of bumps in this case. We also have an incline here of about, I think it's 5% incline or something like that, on which the car is coming. And we can see here that when we start going upwards, the camera takes some time before it follows. Of course, because of the spring damper on it. And then when we reach the top, it will continue upwards because of the inertia and spring dampers again, before it sort of goes down and stabilizes until we hit come to the road where it looks like pretty good here. But we look a bit closer to that, we can see actually that we get some sort of, after all these segments of holes, there is some minor vibration of the camera. We can look at other things like the actual force acting on the camera. So the force is around 10 newtons. Of course, we have the weight of the camera itself, which is 10 kilos, but then depending on the bumps and profile of the road, we will have additional forces. And in this case, we can actually also see the bumps. So this is the bumpy section, right? So these are bumps. It's basically like those white lines that are painted sometimes on the road to slow you down. So that's what I'm trying to model there. So here we have that system with the forces, and we can also look at the force on the wheel. And this is a bit interesting because now what we can see is whenever we get to these segments with holes, and I'll see that better if I zoom in, we actually have a force of 0 newtons, meaning that we lose traction between the wheel and the road. And then it hits on the other side of the hole, and we get a spike here of a force, which probably isn't that nice when you're driving. Okay, so that's how the system works. Now what we wanted to do was design a control system. Of course, we want to design a control system that works for any type of road, not just this particular one. So we won't use this road for the design of the controller. I will disable that and instead go back to the spring damper where I can apply any force that I sort of want to do during the design process. But I also will need this actuator here to be able to control the camera mount. So I enable that, and now I'm ready for the design work. Going back to my presentation, and here we have the same plots that I just showed, but in the notebook. Now, the first thing you want to do is to linearize the model, and that's done with a function called system model linearize. And we have the model here that I'm working with called suspension control. So I do that, and once that's evaluated, we will see a state space model representing the system. There we go. Let's not go into details of this, but it's basically a linear representation of the model in a state space form. But what we can actually, what would be interesting to look at is, let's see if I can scroll down here, for some reason can't, is to compare, there you go, compare how the original model behaves and how the linearized version. So here in Mathematica, I take the original model and I apply to the wheel, I apply a step function, and then I'll plot the movement of the camera and the car. So this is it, okay? So we can see there's some movement. We don't care too much about the details right now, but we see that they are affected by the bump. Then I do the same, but with a linear suspension control model. So it's the same force. And if I do this, we can easily see them that are actually replicating the behavior well. So the linearization that was just done seemed to work very fine for this situation. So now with the linear model available, we are ready to design the controller. First step is to select which type of controller you want. The Wolfram language comes with controllers for state feedback and output feedback. And as you can see, there are a few different kinds in both these cases. And in this case, I will work with the estimator regulator gain. I won't go through the details, but there will come a blog later on that shows and discusses more about the technical details here. But nevertheless, we now want to design the estimator. The first thing I'll do is to get the state variables from the system. So we look at that and we see that it's the camera, position of the camera is the first one, and the velocity of the camera is the fourth one. And as it's the camera that we want to control and maintain stable, what we will do is to create a penalty matrix that puts a big penalty on the position of the camera and the velocity of the camera. So if these two are far are bad, then we get a big penalty, and the controller tries to adjust for that. We, as I said, we will we can start here using an LQ regulator, and we do that using this linear model that we did. So not going through the details here, but let's skip forward a bit and see that we do a few things here, looking at the closed loop system, taking the poles and so on, in order to implement an estimator that we can use. So here we are calculating the estimator gains, and up here the controller gains. So once we calculated these gains, we can now create the complete system. That is done with estimator regulator, which takes our original model. So now we're not any longer working with the linear version. We say, okay, let's use the suspension control model as our input model, and then feedback inputs to the camera mount. So this is what we try to control, right? Using the parameters that we just calculated here. Okay, so that's a quick run through what we of how the system is created, and then we generate the closed loop system also, and I will call that model closed loop system. So this means that without having to do connections, we can look at it in System Modeler, and this is what has been created for us: the estimator, the controller, a force input, and so on. If I double click on this, we can see that this is the model that we were working on before. Now I want to test it with the road. So I set the road to true. And I will still need the outputs here, because I will be using the controller, and I will need the mount here to feed that back in. So we'll go back here to the model. The force now will come from the model of the road and the contact with the wheel. So I'll remove that input. And then we can set up what type of movement do we try to accomplish, or force do we want to have acting typically on our camera. What I will do is to set that to, so it tries to keep it at 0 newtons, meaning in balance. So we connect that to the comparator here, and that goes in. So now I have a system that I can test with my to see how well the controller works. So let me set 30 seconds here before I simulate. I think that's good. there you go. So we simulate it, we get it in experiment browser. And in this new workflow, not only did we create connect the controller automatically to the system, we also added predefined plots, model plots that we can click, for instance, the output response for the Delta cam and the Delta car. And we can see how they behave here, how much they move. It doesn't tell us that much if we don't compare it with something, and we can compare it with how it worked before. So I go to the first simulation where we simulated without, with the same road, but without controller. I plot the camera position, and now we can see that it moved a lot more before we added this controller to the mount. And we can see here that the car, on the other hand, moved basically the same, which is expected. So pretty cool, right? Okay, so returning to my notebook here. This was fast, and I promised that I should mention system modeling in the cloud. And I will. What I've done is here, I published the presentation. You can take your mobile phone and scan the QR code here. That will take you to the Wolfram cloud, or basically to this page here, where you will have this presentation notebook up in the cloud together with a script, which contains sort of what I said during this presentation. I'm not very good at following scripts, but it gives you this story. And you can also, if you have a Wolfram, if you don't have an account, you will be able to view it and read it. But if you get an account, you can also actually make your own copy and evaluate the different inputs and get the results within the notebook. And of course, that works on the mobile phone as well. So welcome to try that. Scan this code with your mobile and go have some fun.